How would Mr. T say it?
How would who?
Mr. T. Anyone? Does anyone know who Mr. T is?
Who's the name?
Lawrence Terode, formerly Army, winner of the Battle of the Bouncers. Going to make me feel old. All right, 36 volts. Mr. T spoke with a very harsh, deep tone. It's 36 volts, fool. If you want to call me a fool to my face, if you do it in Mr. T's voice, I'm good with it. If you're not quite sure what Mr. T sounds like, ask your parents. I'm willing to bet your parents know. All right, so as I go out another meter, 2 meters away, what's the electric potential there?
Volts. 18 volts.
Another meter out,
12 volts.
another meter out.
9 volts.
All right, and so on. So notice as I get further from a positive charge, my electric potential gets smaller. If I put a positive charge here, which way will it go? I got a positive charge there. I stick a positive charge here, we know, right. So we have a generalization of a positive charge moves to a lower electric potential. Similarly, a negative charge moves, I guess I should say wants to move. Wants to move to a higher potential. Now I'm just using the word potential. Officially it's electric potential. There's also gravitational potential and so forth. And so this in combination with electric potential, let's see, potential created by positive charge goes down as R goes up. And potential created by negative charge, potential created by negative charge goes up as R goes up. Because if this were negative 4 nanocoulombs, that'd be negative 36 volts, negative 18 volts, negative 12 volts, negative 9 volts. And so as you move this way, becoming less negative, in other words, increasing. So there's the fourth explanation for why opposites attract like repels. But we haven't talked about voltage. So let's talk about voltage. If I take my positive charge here, my positive charge moves to there. What is the change in potential?
Negative 6 volts.
If I start here, and it goes to 12, then to 9, and then back to 12, and then 18, and 36, and then ends up back on 12, what's my change in potential now?
Negative 6.
The whole thing. Volt. So it doesn't really matter the path it takes. I know it's just going to get from one spot to another to get to the exact same, if it starts and ends in the same place, it's the same change in potential. This change in potential that an object would go through, or that exists whether the particle moves there or not, this is voltage. The electric potential difference and voltage are synonyms. Because the actual value of an electric potential really does not matter. What matters is the potential difference in order to figure out how much oomph charges are going to get to move. So if I have a battery here, and let's make it 12 volts, that's my positive side and that's my negative side. It does not tell me the potential at either the top or the bottom, it only tells me the difference. So if the bottom here is 0 volts, what would the top be?
12 volts.
If this is 100 volts, what would the top be?
112.
112. What did you say?
No.
And so all I know, and all that really matters, is that the high side is 12 more than the low side. So if I have a charge that moves from here to here, well, first off, if I have a charge moving from there to there, is it a negative charge or a positive charge?
Negative charge.
Most likely. From a potential point of view, negative charges move to a higher potential. Or it's going away from negative towards positive. Well, you know, you got 4 different ways of explaining the same thing. If I want to figure out how much energy was used in order to do that, well, I have a relationship between U and V. I know that delta U divided by that test charge is going to be equal to delta V. So the change in potential energy is going to be Q delta V. I know that the charge moved through positive 12 volts there, so that's positive. Q, well, it's a negative charge, so I'm going to make it negative 0.1 coulombs, just to make the math easy. So I end up with a total change in potential energy to be negative 1.2 volts. Well, does that make any sense? If I put a charge here at rest and it started moving this way, would I expect my change in potential energy to be negative?
Why is it volts? What would a coulomb volt be? Just joules.
Thank you. Jules. And Ben, were you nodding to answer my last question?
Can you repeat it one more time?
All right. I got my positive and negative ends here. I got an electron, I let go, then an electron moves up to here. Is it reasonable to expect that the change in potential energy is negative?
So,
Why?
because it's effectively moving towards the positive charge, so
Right.
potential energy is getting less between those two.
Are you saying that because it's negative or for some other reason? Why would you expect the potential energy to drop?
Kinetic energy increases.
Yeah. And we're dealing with conservative forces. Now, if you have a battery and you have electrons here that can migrate all the way up there, you probably have a dead battery. They aren't supposed to do that. There's supposed to be a barrier inside batteries that prevents any charges from moving one way or the other. For the rechargeable batteries, it allows, if you add enough potential, you can force charges through the barrier, but every time you do that, it sort of weakens the barrier and eventually the rechargeable battery doesn't really recharge much anymore. Questions here? Because I'm about to connect that thing that I wrote over here, connect that to what we're doing right now. is. So I know that we have this du. I know that the change in U is equal to the charge, the change in potential energy is equal to the charge times the change in the electric potential. Or, if we're dealing with infinitesimally small changes, du equals qdv. I can plug that in for du here. And so I have my electric field is equal to, well, the q's will cancel out. And so what I'm left with is dv dr r hat. If the electric field is constant, then, so if the electric field is constant, then the electric field is equal to the negative delta V divided by whatever distance you're talking about. So over D for distance. And we can then work that into the change in the potential is just equal to negative ED. I will occasionally refer to this as the Ed formula, not to be confused with Ed's disease. So all we need is a situation with a constant electric field to make this worthwhile. And wait, parallel plates. I think we did cover that last time. Parallel plates that are close enough to be so that we can consider them infinitely large. And again, recognize we've only talked about one physics formula. All the rest is just math and definitions. We will eventually get to another physics formula. Chapter 30. So, if I have a 3 nanocoulomb charge, and let V equal 0 at R equal to infinity. I know that my electric potential drops off like a 1 over R relationship. My electric field, so that's V versus R, my electric field is just the derivative of V, the negative of the derivative. Well, my derivative starts out as a large negative number, and the negative of that make it a large positive number. As V gets smaller, that's a V, not an X, as V gets closer and closer to 0, well, so should the electric field. So it's this is a 1 over R squared relationship, which we knew already, but we also have that relationship of E being the negative derivative of V with respect to R hat. And it works there, obviously. We will eventually apply it to more complex situations. If the electric field is 0, so let's say that we take a conductor. Excess negative charges. That would be the radius of this sphere. So let's do electric field first. Excess negative charges. Inside what is the electric field? Conductor.
0.
Yeah. So my electric field is 0. When I get to the surface here and I transition, then I can treat it like a point charge. And so it'll shoot down to something negative and look something like that. The red, as people call it today, the red is the plot of the electric field from this spherical conductor. Well, let's look at potential. I know the electric field is the derivative of potential, in other words, or the negative slope of potential. Outside of this, it's a 1/r relationship. So that is my V plot. What happens when I get to the surface here and I start moving closer to the center? What does that tell you? What happens with the potential?
Should be higher.
As in higher this way or higher, more negative?
I'm not sure.
Anyone else?
More closer to 0.
It should be around 0.
Yeah.
Anyone else? You agree? All right, so let's first take a look at if it goes something like that. Remember that the electric field is the slope, negative slope of it. The slope is negative there, becomes less negative. So the electric field would be positive, right? Let's see, so if that's a negative slope, then the electric field would be positive, and so the electric field would look like that. Something like that. But my electric field is 0, so it can't be changing like that. Why do you say that the potential would be 0?
Well, it doesn't make sense now that I think about it, because if the potential would be higher, or I guess in this case lower, or more negative,
So go down.
from R to go, it's like almost, I think the same way as.
That would just continue going.
No, it'll jump back up to.
All right, so it's gonna come down like this, and when I get to R, it's gonna jump back up
To 0, and then
and then flat line.
no, and then go back down.
Oh. Something like that.
I guess it was flatline.
Flat line? Is that what you said?
Yeah, because the whole inside's 0. So.
All right, so we've got, and I think this is what a couple other people were agreeing with. All right. What about this part right here, though? That sudden jump. What would that tell you about the electric field? Let's look at a mechanics relationship. I think this is a math question. I know that displacement is, try that one again. I know velocity is the derivative of displacement with respect to time. If my velocity is 0, similar to my electric field being 0, if my velocity is 0, what does that tell me about my position?
not changing.
So over there, if my electric field is 0, what does that tell you about the potential?
It's not changing.
It'll flatline. The slope is 0. But it doesn't change. And so you'll get that bend right there, and then suddenly it just keeps going.
That's the graph.
Yeah, and I unfortunately changed colors there. Green. So my electric potential would drop off and shoot there. Electric field would drop off to 0, drop off to 0. My electric potential is steady. So the electric potential inside this, where the electric field is 0, it's known as equipotential, equal potential. And it really doesn't matter where I come in, which direction I go through, because given our scenario here, these charges are all distributed around the outside. And matter of fact, the charges will always distribute around the outside until the outside is equipotential. At every point if it's in electrostatic equilibrium, every point on here will be at the exact same potential. So we have surface of electrostatic conductor in the electrostatic equilibrium is equipotential. How many of you have done Calc 3, finished Calc 3? And in Calc 3? And Sarah?
I'm not thinking.
Okay. The term NAPLA, meaning